So in previous lectures we have started module number 5, and module number 5 consists of memory registers, aspects of system timing, testing and verification. Out of that we have seen system timing considerations, then we have discussed about the 3 transistor dynamic cell, then we have discussed the single transistor dynamic cell, and then we have discussed about the pseudo-static RAM cell. Okay, so we have discussed about the various issues. We have compared them with respect to area, power dissipation and volatility. So another technique we are going to study, or another energy storing element, another type of memory storing element or memory cell, we can say that is the 4 transistor dynamic CMOS memory cell. So in the today's lecture we are going to study about the 4 transistor dynamic cell, then 6 transistor static cell, then we are going to discuss about the JK flip-flop, and the JK flip-flop is used as a T flip-flop and D flip-flop. Okay, so we will discuss about this 4 transistor dynamic cell. So what is this 4 transistor dynamic cell? The cell here includes both N-type and P-type transistors and are intended for CMOS system. So it is used for CMOS system. So it uses both C-type N-type transistor and P-type transistors. Both the dynamic and static elements uses 2 buses per bit arrangement, so that the bit is available in both normal and complement form on the bit and bit dash bus. Okay, actually here it is bit line and this is a bit dash or bit bar line. Okay, so there are both the static and dynamic elements. In case of both, that is static and dynamic element, so this is for dynamic element. So the 2 buses are there. These are the 2 buses. They are in complement form. It is bit and bit bar form. Okay, so prior to reading and writing information, operating the data, the buses are pre-charged to VDD or at logic 1. Okay, so whenever we are going to storing the data or reading the data, so previous to that we have to pre-charge the bit lines. Okay, so we have to pre-charge this bit line and this bit bar line. So for that, to pre-charge the bit and bit bar line, we have to use the transistor T5 and transistor T6 is used along with phase phi 1. Okay, so it is pre-charging is coincident with the phi 1 clock cycle. Okay, pre-charging, so this bit line and bit bar line are pre-charged to logic 1 level. That is, when pre-charge line will be high, the VDD is connected to the bit line and bit bar line, and hence both lines are at logic 1 before reading or writing. Okay, then we will discuss about how to write the memory cell. So to write one, there is a one write operation and one other is a read operation. We will see how to write the memory cell. So to write the memory cell, so we will consider this is the upper part of the memory cell. So this is your memory cell and this is a sense amplifier. This is sense amplifier and this is memory cell. So this memory cell consists of the 2 transistors T1 and T2, and they are arranged to give a complementary form. They are arranged to give a complementary form. Okay, and T3 and T4 transistors, they are used while reading and writing. So it is called a row select line. Okay, and there is a column select line. Into this column So these are the horizontal cells. This is one horizontal cell, another horizontal cell. Likewise, you will get the different cells. For one column, there is a one sense amplifier. Okay, and the sense amplifier so will be made active by applying the sense voltage here. Okay, we'll discuss about after that. After first, we'll discuss about the how to write the operation. So to write, so we have to select a particular column by applying supply by applying the high signal to the particular column. So that is, we have to apply high voltage here, and it is coincident with the phi 2 clock signal. It is a coincident with the phi 2. This is also coincident with the phi 2 clock signal, and this write operation or the row select operation, it is row select and column select operation are along with the phi 2 clock signal. Okay, and so already these lines are precharged to the logic high, and depending upon the data value onto the IO bus. Okay, so particular line will be discharged. If suppose the IO bus, this is IO bus and this is IO bar. If IO bus is equal to 1, so IO bar automatically it is equal to 0. Okay, so therefore this is 1 and this is 0. As this column is activated, so already this is 1, this is 1, there is no discharge occurs. And if it is 1, then this will discharge via IO bar bus. Okay, and hence this IO lines will be acting as a current sink here. I will like it acting as a current sink. Okay, now so this will be at this bit line will be at logic high, and this bit bar line is at logic 0. Okay, now at the same time when the column select line is high, at the same time row select line will be high. Now we want to store the data, and the data will be stored onto the gate of transistor T1 and T2. How? So if we apply row select line will be high, the transistor T3 and T4 will be turned on. Will be turned on. Whatever the data here. So this is we have assumed here, that is IO bus is equal to 0, 1, and IO bar is equal to 0. So hence bit line is equal to 1 and bit bar line is equal to 0. So this 1 will be stored onto the gate of T2 capacitance. Okay, and this 0 is stored on the gate of T1 capacitance. Okay, so whatever the data present on bit and bit bar line, that will be stored in the gate of T1 and T2 transistors, and they will be in complementary form. So in this way, a write operation will be done. Have you got the write operation? Okay, so write operation will be done at the starting. The bit line and bit bar lines are precharged, then column select lines will be on. So it will one of the bit or bit bar line, either of the one, it is discharged through the bus. Okay, as the bus will be acting as a sink. Okay, and then at the same time row select line will be activated, and the data on the bit will be stored onto the gate of T1 and T2 capacitors. So this is the write operation. Now read operation. In case of read operation, again we are going to precharge this T5 this bit line and bit bar line by using transistor T5 and T6. Okay, both bit and bit bar line is precharged to logic 1. Okay, and then row is selected, so row line will be make high. Okay, now if suppose Already the logic 1 is stored as per our previous assumption. Logic 1 is stored onto the gate of the T2 and logic 0 is stored onto the gate of T1. Okay, so that will happen. The transistor T2 will turn on. Transistor T2 will turn on and it will ground this line, and this, as it is 0, this will be make is equal to turn off the transistor, and hence this will be maintained at logic 1 and this will be maintained at logic 0, and then so logic 1 and logic 0 will be sensed and it will be given onto the IO bus by using column select line. Okay, so in this way we can do the read operation. And then what is the use of the sense amplifier? So sense amplifier already, so in case of memory element, so we are more interesting in case of the area of the memory. So area of the memory should be less, or the area required to store 1 bit of information is should be as small as possible. For that, so the transistors, so these transistors T1, T2, T3, T4, all these transistors are make as small as possible, and the current driving capacity in that case is very small, and hence it will take more time to charge the line and more time to discharge the line. And in case of the read and write operation, it will be not done in one cycle, it will require 2 cycles to read operation. So increase the charging capacity or to increase the current handling capacity of, that is delay time in charging and discharging of this bit and bit bar line, we are going to use the sense amplifier. The sense amplifier, it is nothing but a sense flip-flop. The T1, T2, T3, T4, they are acting as a sense flip-flop. Okay, when the sense line, this is sense line and this sense line is equal to 0, at that time all the transistors will be off. Okay, and whatever the data here, that will be stored onto the gate of T1 and T3 transistors, T1, T2, T3, T4 transistors. Okay, see here, so this bit line will be stored onto the gate of the T3 and T4, and bit bar line will be stored onto the gate of T1 and T2 capacitors. Okay, now how it will sense the data, okay, now if we apply logic high signal, then this transistor will turn on, that is T5 transistor, and this T5 transistor will turn on. And so here, as we know that already we are assumed, that is here it will be logic 1 and here it is a logic 0. Logic 0 it is at here, so T1 transistor, so at here it is 0, T1 transistor will be on. And what about this transistor T2? T2 transistor will be off. Okay, and what about this T3 transistor and T4 transistor? Logic 1 is there, so logic 1 is there, T2, T3 transistor will be off and T4 transistor will be on, and hence so T1 transistor is in on condition and T4 transistor is in on condition. Okay, as a T1 transistor is on, so VDD is applied to bit line, and bit bar line is grounded through T4 and this sense amplifier, this transistor. Okay, it is grounded, and hence this will be make. Okay, before sensing whatever the data stored onto the bit and bit bar line, they are precharged at the intermediate level. This bit line and bit bar line are precharged at the intermediate voltage, and then when we apply sense voltage, depending upon the data stored here, if here it is logic 1 is stored, here it is logic 1 is stored, and here it is logic 0 is stored onto the gate of T1, T2, T3, T4 transistors, and they will turn on If logic 0 is there, turn on T1, and if logic 1 is there on this, so it will turn on T4 transistor, and hence VDD is applied. Okay, so VDD is applied to bit line and bit bar line is grounded. Okay, in this way we can sense whatever the data stored. Okay, so this is about the 4 transistor dynamic memory cell. Okay, so this is the same whatever we have discussed here, and then we will discuss about the 6 transistor static CMOS memory cell. Okay, what is the difference between the static CMOS cell and dynamic CMOS cell? 4 transistor dynamic CMOS cell, it is the same arrangement is there, same transistors are there, but the 2 transistors are replaced. T1 and T2 transistors are replaced by the 2 inverters. So these 2 inverters are connected back to back. Okay, and data will be stored onto the gate of the respective. This will be the gate, input gate. Okay, and the data will be stored onto the input transistor, and this will be the data will be stored onto this input transistor, and that will be then in complementary form. The same you will get here. Okay, the figure shows the 6 transistor SRAM with the adoption of the dynamic cell and modifying into the form of the static memory cell. So previously the previous whatever the 4 transistor dynamic cell, it is converted into the static dynamic cell by the use of the 2 inverters. It includes the additional transistors per store bit. Thus it is called as a 6 transistor dynamic cell. So these are the 2 transistors. Inverter contains 2 transistors, this inverter contains 2 transistors, and hence the total cell, it is the 6 transistor dynamic cell. Okay, the transistor T5 and T6, the transistor T5 and T6 are acts as a access, which is the for a memory element which is formed by the connecting the 2 inverter back to back. Okay, these are the, okay, here T1 and T5 and T6 are there. T1, T2, T3, T4, these are the 2 transistors, 2 inverters. So for inverter 1, T1, T2 transistor, T and T3, T4 transistor are for inverter 2. T5 and T6 are used for the row select. Okay, and T7 and T8 transistors are used for precharging option. Okay, the whatever the arrangement, it will be the same, or working of this transistor or of this memory cell is the same as the 4 transistor dynamic cell. Only thing is that we have made this memory cell as a static memory cell. So similar 4 transistor dynamic cell, dynamic RAM, the information is stored into the memory cell, and the memory cell is connected in such a way that it gives the complementary states when the row select line is activated. When the row select line is activated, at that time you will get the 2 lines will be in complementary state. Okay, when the row line is deactivated, the data is stored remains in the memory cell. When this row line will be deactivated, at that time the data will be stored onto the gate of these 2 these 2 inverters, and they are given feedback, and there hence the data will be remain constant and the data will be remain static. Okay, so this is another form of the non-volatile memory. So previous 4 transistor memory cell, it is the decaying one, and hence the data onto the gates of the previous 4 transistor dynamic cell, it is going on decreasing, discharging, but here it is not possible. So here you will get the data is stored in the complementary form, and they are connected in back to back, hence it will be remain constant. So this is the non-volatile memory. Okay, this is about the 4 transistor dynamic cell and 6 transistor static cell. Okay, then we'll discuss about the another element, that is again memory storage element, that is the flip-flop. So it is the memory element. Flip-flop is again one type of memory element. It is widely used arrangement of the static memory element. Also with the JK flip-flops, arrangement can be obtained such as we can do the T and D flip-flops. So JK flip-flop also we can modify to form T and D flip-flop. Okay, the flip-flop has two inputs, that is clocked J and K, along with the asynchronous clear input is there. Okay, so J, K and clock is there, along with the asynchronous clear input is there, and it has two outputs, that is Q and Q bar, or Q and Q dash will be there. The input J and K are read from the rising edge of the clock signal. J and K are the read on the rising edge of the clock signal. Okay, and the data is passed to the output Q and Q bar onto the passed to the output on the falling edge of the clock. Okay, note here the JK is implemented in master slave configuration. Okay, so JK is implemented in master slave configuration. So in order to solve the race condition, okay, you know the race condition, and to solve this race condition we are used a master slave configuration here. Okay, we have to use or we have to design the JK flip flop in master slave configuration. So gate implementation of flip flop. So we can implement the gate JK flip flop implement. We will write the expression for the JK flip flop. So the expression for the JK flip flop can be implemented using either NAND logic and NOR logic. Okay, we can implement by using NAND logic also, or by NOR logic. So by with the help of the equation. Okay, if the NAND arrangement is used, you know that the NAND arrangement, it will take more area because it will require to form NAND. So we to implement any equations we require the more area, and it is also seen that when it is connected in series the overall delay increases, and in practice not more than 4 transistors connected in series. Okay, and hence NAND configuration is less used. However, the number can be increased by including the buffer in between the next 4 transistors. Okay, also it is seen that the performance of the NAND gate is slower than the NOR gate. So hence these are the some of the drawbacks of the implementation of the JK flip flop by using NAND gate. Hence we can use the implementation of the JK flip flop by using NOR gate. Okay, so NOR gate implementation can be easily done. Okay, as it has connected in parallel. Okay, NOR gates, so it has the parallel transistors, and hence it will reduce the power dissipation. Also it will decrease the time delay. Okay, it decreases the area. It has some advantages by using the NOR gate implementation. Okay, then next, the switch logic and inverter implementation. So for the JK flip flop, the switch logic, and we can use the we can implement JK flip flop by using switch logic, as well as we can use the inverter logic. Okay, if n pass transistors are used to realize the logical requirement, it must be kept keep in mind that, okay, so we have to keep in mind that, so there should not be more than 4 pass transistors connected in series. Okay, so that is our, we have discussed what are the requirements of the subsystem design. Okay, so there should not be more than 4 pass transistors. Okay, so there will be the threshold effect is going to be occur here, and another 1 pass transistor should not drive the gate of the another pass transistor, because the logic level is going to be degraded. Okay, and hence this will be, we have to keep in mind. Okay, also we can implement D flip flop and T flip flop by using JK flip flop. How D flip flop will be implemented? D flip flop can be formed from JK by connecting an inverter in between both inputs. Okay, inverter we have to use in between the two flip flops or two inputs. And then T flip flop can be readily formed by using JK flip flop, that is connecting J and K together to form the T flip flop. Okay, so this is about the JK flip flop implementation, and in the next lecture we are going to discuss about the testing and verification. Okay, so we'll stop here for the today's video.